Pramod Kumar. I'm currently a PhD scholar at IIT Madras. So, as Sir said that I have been dabbling on FEniCS since last 3 to 4 years. So, basically, my core research area is computational mechanics with lithium-ion batteries, the system of interest, especially the active particles and the chemomechanics diffusion that is happening. And now here along with me is my colleague Dr. Rishikesh, the former PhD student from IIT Madras, and now he's a postdoc at uh, KIT Germany. And I would like to thanks first of all organizers Professor Ratna Kumar Anavutula, Professor Anand Krishna Kanjala, and Professor Tupesh Nasre for allowing us to deliver this talk. Yeah, so with that, I would like to proceed. Yeah, so as Professor mentioned, this will be a very interactive session. So whenever you have doubts or anything, just feel free to ask. Most of them will be demo based. Firstly we'll give a brief overview of the FEM. Brief overview of the FEM, followed by some of the tools which we will be using, mostly the FEniCS. Uh, Later on, GMesh is something 3D software for meshing, where we can make the geometry of our desired shape, and then we can use that as an input to the FEniCS as a mesh, and then followed by the Parallel, where we can do post processing or visualization mostly in the form of the files of those will be of the PVD or VTK format. Once we briefly introduced about the tools, we'll be giving more. We'll be setting up the system. When I mean the setting up the system, we'll help you with installation. So initial stages of our work, probably we faced setting up the systems in setting up this FEniCS installation and everything in Ubuntu or Windows system or in cluster for that matter. So we'll give you our insights and a brief. For some time, Dr. Rishikesh will help you with how to set up the system in your personal laptops. And this is where our real examples will be talking. So as of now, we have planned of 4 examples, but if time permits, we can extend to 5 to 6 examples. Or if time doesn't permit, we might stop at 3. So basically, the rationale behind choosing these examples, firstly, linear 1D example will will get you going, will put you into the grooves of how to go ahead with the FEniCS, and then we'll show okay how to extend the 1D example with just trivial modifications for 2D problems. So both of them will be a scalar example, followed by we'll be going to the vector problems, our classical elasticity, solid mechanics, small strain problem. And then we'll also explore the nonlinearity, how we can use it in FEniCS with simple 1D examples. And then the fourth one, the transient problem, where we'll be talking about the time-dependent phenomena, which we encounter usually, in heat transfer problems and many more elastodynamics for that matter. But we'll be considering only the first-order time derivatives. And if time permits, we'll go with the multiphysics and biomaterial problem. And then followed by some of the references later where you can go back and see the books and related forums where you can, for advanced applications, you can ask question and answer sessions and then get your things going. So just to give you the brief introduction, we have a physical system. So the physical system is essentially the things that are happening in the real world. We want to gain insight, and it's not always possible to carry out cumbersome experiments due to time constraint, due to other resource issues and everything. So we idealize that physical system into something known as mathematical model. So the model offers the rich variety of the insights that is happening in those systems. For example, just dropping the ball on the floor from certain height. So we'll be using classically F equal to ma, Newton's second law, in order to compute the qualities of the interest and see what is happening with the system. So this is just a trivial example, to convert the physical system into the mathematical model. So then the question remains how to solve the mathematical model. So most of the times, invariably the mathematical models will be in the form of system of PDEs, ODEs, and PDEs. Rarely they are form of your linear algebraic equations. So FEM comes into picture here. In a bigger picture, in all this, the FEM comes somewhere here. So you want to convert the given the mathematical model into a discrete model, which will be far more easier to solve us. So there is where FEM. So just to give you that FEM is not the only technique. There are other popular techniques as well, such as FDM, finite difference method, finite volume method, discrete element method, and many more. But FEM is much more popular because of the way it handles the boundary condition, the complicated geometries. So for those things, FEM has been one of the popular systems. And then once we get the discrete model, we'll get the discrete solution, and then we'll try to see it how it matches well with physical system and see what all the insights we can get. So yeah, in the overall bigger picture, FEM sits somewhere here. Our goal is to solve the mathematical model and to get the solution and then analyze the physical system. So that's where the FEM sits in, and FEM is not the only tool. There are other popular tools as well, but FEM surpasses in few aspects over them in certain aspects. Yeah, so this is where FEM fits in. So in summary, in a sense that we have the physical information, so something happening in the real world, we idealize it with the governing equations and boundary conditions. So how the system is governed by these sort of equations and boundary condition. So there could be errors associated here as well. We may not be capturing certain phenomena that those are happening and everything, but barring those aside, assuming that we have been given a mathematical governing equations and boundary conditions. So our job is to solve and get the solutions and see how the system is behaving. So that's where finite element method comes in handy. So I mean, this is only one of the numerical methods for solving PDEs. This is not everything. I mean, FEM is one such very popular tool. So it reduces the system of PDEs. It need not be, I mean, the physical system need not be just one governed by one PDE or something. So it can be system of PDEs, especially in class, the multiphysics problems. So those reduces the PDEs to your algebraic set of system of equations. Something known as, you do the discretization of the domain, and then you can write the weak form. We are assuming that you have probably done some basic course of FEM, so these terms may not be alien to you, discretization and weak form. Nonetheless, for the sake of completeness, we will be giving a brief overview of those, but that's a course in itself. We'll not be going too exhaustive in it. We'll just give a brief overview, and then we'll get on to the demo as early as possible. And so essentially for that, we need to discretize our interested domain, the domain, the physical space that is happening, there the phenomena are taking place. That domain will be discretizing into something known as elements, subdividing the bigger domain into smaller chunk of, something known as finite elements. So, so this is what the FEM, I mean, some of the ingredients of the FEMs are, or the purpose of the FEM is. And the FEM, the application, some of the applications, some of the notables, but not limited to solid mechanics, which me and Dr. Rishikesh works in, heat transfer, and, fluid mechanics as well, for also the stock market predictions, for that matter, quantum, determining the quantum states of the electrons and everything. So wherever the governing equations are there, wherever you have the PDEs, and wherever the analytical solutions are not usually feasible or not possible, in that case, we resort to one such method known as finite element method. Yeah. So and okay, where does the FEM sits in a bigger real picture is somewhere here. And so why the FEniCS and where does it sit? So the FEniCS is one of the now picking up one of the most popular open source software. When I mean the open source, you need not pay anything to the FEniCS developer community. It's a computing platform. It's based on finite element. It works basically finite element, and so you can code both in Python and C++. But in our this workshop, we are only going to focus on Python, because Python is one of the our purpose is to make the system. Our purpose is not to make the system more efficient or something. We just want to implement those system of PDEs and get the insights into the model. So that's and Python is much more human, closest to human readable format, understandable, human understandable language. So that's why we will be sticking with Python, and that is one of the reason why FEniCS is much more popular. And and then also one can ideally code in C++ as well, although personally I haven't explored that. And our this workshop is restricted to Python. So yeah, see, personally, for my research, I have used the FEniCS and abacus. I am platform agnostic. As far as the things get done, I'm fine with that. But I wish to give you the bigger picture. Where does the FEniCS stands? FEniCS versus some of the other popular commercial software, as far as at least the solid mechanicians goes, the abacus, answers, COMSOL, etc. Firstly, the major advantage is FEniCS is open source, whereas the abacus, answers, and COMSOL, you have to pay hefty amount in order to buy their licenses. That's an advantage. Secondly, as the workshop progresses, you will be seeing how easy it can be, in order to solve certain problems. One might question, and why not? I mean, some of the people you might have coded, in your coursework or in your research in MATLAB or Fortran or some sort of other languages, which are pretty fast as well. If we do it really them properly, but yeah, the scaling of this FEniCS is quite.
Somebody seems to have a question. Karthikeswar Vivedi.
Yeah.
Yes, no, sir. Actually, I was trying to. I was checking, sir, option. Okay.
No problem. Fine.
Oh,
yeah.
okay.
Thanks.
Yeah. So yeah, where does the FEniCS stands compared to abacus and answer? See, abacus has certain advantages. Some of your contact algorithms are really very robust. Doing nonlinearity, especially the constitutive related nonlinearity such as plasticity, can be quite, especially for established model, can be quite an easy job in abacus or answers. Your large deformation, your shell elements, doing those things can be quite easier. The learning curve is not as steep, when you do code from the scratch in the software abacus. Those are the advantages, but certain disadvantages if you have your own, if you have come up with some model or some sort of equations, you have to coupled equations you have to solve, and it may not be always, those modules may not be available in abacus, answers, or COMSOL. So in such case, you can resort to FEniCS. So that's where the FEniCS stands. And now, as it being open source, there is a healthy community that is supporting, and people are coming up with their own projects, with their own advances, with their own tools, plugins, in order to make things easier. Yeah. So what is a tenet of FEniCS? On what basis it works? I would, if I have to summarize, it works on just you give the variational form, the abstract variational form in Python, which will convert, in the backend using its own tools such as Dolphin, FFC, Fiat, and UFL into complicated probably C++ and algorithm, and then it assembles, and then it gives out the solutions to us, right? So the user interface, at least as a beginner level, is very easy. Just you code it in Python. Most of us might be very familiar with the Python, code it in Python, and then just let the FEniCS take care. So some of the components, see, although these components, you need not worry about these components, but you might, come across these name of these components on the web, or whenever you ask a query in forum or something. So just I just wanted to highlight these components, such as known as Dolphin, FFC, FEniCS form compiler, Fiat, UFL, so these are what make FEniCS work faster, and these take the Python code and then convert into appropriate C++ code, assemble them in an efficient, fast manner, and then give out the solution. And so that is the thing. So yeah, just for the, so this is how the logo they have maintained. So this is the website, FEniCS project. This is maintained well. You can go and just explore it at the later point of time. You can download the setups. We'll go to this website and download installation. We'll do that.
Hello,
Dr.
Pramod.
Rishikesh will help us. So this is how this is a classical our Navier-Stokes equation in its weak form, right? So just I wanted to show you. So this is how it is, as simple as this. Put this equation, code this in FEniCS. Before this, just add the domain. Mesh. Hello, sir.
There is a question.
Yes, sir.
Can you comment on the limitations of FEniCS as a computing tool? And also another question, how is this software different from MATLAB?
Yeah, thank you for the question. Yes, first of all, the limitations, in some sense, at least for beginners, it can be a black box. You don't know what are the entries of, you can know the entries of the stiffness matrix, but it involves a lot of, computer skills, coding skills. So it may not be that trivial always. Error bugging can be difficult if we don't know where things are going wrong. If everything seems right in weak form, still things can go wrong. So tracing the source of the error and non-linearity can be very much difficult. So that's the one part. And the second the part of the question was how it is different from the MATLAB. So the MATLAB, if at all, the way I have coded in MATLAB, the assembling and at least as far as the linear problem goes, if it is the domain is too big and number of elements are too high, the most expensive part is usually the assembling the global stiffness matrix and then solving it. So those part in MATLAB can be very expensive. Secondly, the MATLAB, you have to start from the scratch. I mean, you have to load the domain. You have to, here as well, we are loading it, but we need to perform the numerical integrations all by ourselves. We need to do the assemblies by ourselves. We have to code for everything. We have to choose, after choosing, we have to have the subroutines associated with your shape functions and everything. So, and as well, secondly, MATLAB is a commercial as well. You need to pay for it. And thirdly, usually the MATLAB doesn't do that great serially, at least. I have coded so far serial itself. So for example, I wish to give one example where, if I have to do some sort of multi-physics problems, I have done myself, I'm a bit experienced in multi-physics problems. So lithium-ion batteries where I wanted to study, active particles. The MATLAB performance was, the same system of equations when I'm solving on MATLAB with the same number of elements. The MATLAB code was taking around 2 days serially. The same code in FEniCS.
Pramod,
yes, sir.
May I interject? I think the question is not about the speed, but in terms of philosophy, right? MATLAB is a general purpose interpreted programming language wherein you can, if you want to solve a finite element problem, you have to write all the code by yourself, whereas FEniCS will have definitive modules that are readily available. You just have to load the module.
Yeah, yes, sir.
Right. I think that is the kind of comparison.
Yeah.
I think that's what they're asking. And that is my understanding.
As sir said that, so MATLAB is more general multi-purpose platform. And whereas the Python, I mean, the FEniCS is just, only for specific finite element method. I hope that answers your question. Yeah. So, this is a weak form. So some of the tools which we'll be using it, just to make, most of them, I mean, we will not be so extensively using them, but nonetheless, in a case of, advanced applications where you want to make complicated geometries and then later on visualize things and everything. So for that, we'll be using the GMesh. It's again an open source, an FEmesh generator. It generates both in 2D and 3D. Just pardon me. And then one of the advantage of then you can, again, the tools with parametric input, you just need to load some text file, and then you might need to change the mesh size and everything. You need not even interact. Once you have the basic code, you need not even interact with the GUI, and then you can get a very fine, complicated sort of mesh. And then these mesh can be converted by FEniCS readable, FEniCS readable convert using Dolphin Convert, some sort of command, which we will be showing you in the subsequent slides, in the subsequent demos. So this is what the source of. We'll be installing this as well. And then the ParaView again maintained by.
Hello, Prama.
Hello. Yeah.
Yeah, there is one more question regarding ANSYS.
Yeah.
Yeah. How is it different from FEniCS in comparison with fracture mechanics problem?
Yeah, thanks for the question. Yeah, first of all, I don't have an extensive experience in ANSYS. So the fracture mechanics, I don't know which are the modules available, but I think in abacus there is an XFEM, but I don't know anything regarding the fracture in ANSYS. What are the tools available? I'm not aware of it. Yeah, so that's the answer. I hope that.
Also, one more question.
Yeah.
Do I need to learn Python to use FEniCS?
Yes, Python. Yeah, rudimentary Python is essential in order to learn gain the best out of the FEniCS. Yes, Python is necessary. There are, I mean, it provides either in Python and C++, but if most Python is much more easier, and the curve involves is not as steep as C++. So yes, you need to learn. You need to know basic Python. Even if you don't know, I mean, don't worry much about it. At least the examples we will be treating are not Python intensive. So yeah, you should still be fine with that. Yeah.
Paras Kumar, you can also ask your question.
Yeah, thank you. Can you hear me?
No, I'm not. Your voice is not so clear to me. Hello.
Hello, Paras Kumar.
Yeah, can you hear me?
Yeah, now I'm able to hear you.
Yeah, okay. So could you please comment a bit about like how does this FEniCS compare to other open source C++ based libraries, say such as Deal2 or something?
Yeah.
Because I've been using like Deal2 now for almost 3.5 years. So I was a bit curious to know, like, would it really make my life simpler if I switch to Python and FEniCS?
Yeah. See, honestly, I have not used Deal2. So I don't know. I can't answer your questions really. But as far as from the discussion or from vague discussion, vague readings, I remember Deal2 involves a very steep learning curve initially, especially. But there are certain advantages Deal2 provides over the FEniCS. Access to your stiffness matrix entries, and I think Deal2 parallelization is much more robust than FEniCS. But again, these are all my surmises, guesses. I exactly don't know.
Okay, so like a follow-up question. So how much intrusion does FEniCS allow at the element level of assembly or something? Like,
as a beginner,
I go at the assembly level and play with the matrix or something?
Yeah, as a beginner, that's very probably it doesn't. It's no. It doesn't allow. It's not as intrusive as you would expect Deal2 or MATLAB for that matter. But yeah, it doesn't. But probably as an advanced user, you might be able to go back and check few of the things.
So it's possible to do it.
Yeah, it's possible. I have seen people doing it, on online forums and everything. But I have not done myself.
Okay, thank you.
Yeah, you're welcome.
Shakti Kumar, now you can ask your doubt.
Yes, sir. Good evening, sir.
Yeah, hello. Hi, Shakti.
Yes, sir. Sir, in abacus, is there moving heat sources included in this workshop?
So we have the heat source. One example,
yes.
Heat transfer related.
Sir, we are working on material science in laser surface modification process.
Okay.
So, sir, moving heat is so important in this for the simulation purpose. So, sir, I am asking for this.
Yeah. So what kind of simulation are you doing? Are you doing transient heat transfer? I mean, in that the source is moving. I assume. Is that what you mean?
Means, sir, suppose we are doing cladding, okay, laser cladding process.
Okay.
And the temperature distributions are mainly and effect of temperature on the stress develop.
Yeah, so we are showing one such example of something linear thermoelasticity, where our temperatures are affecting the stress buildup in the domain. Yeah, so you may want to wait till then, and if you see that example, things might be much more clearer to you. And yes, those multi-physics problems can be possible to solve in FEniCS.
Yes, sir. Okay, sir.
Yeah.
Hello, Pramod.
Yeah.
There are some other questions in the chat.
Yes, sir.
Can we solve fracture mechanics problem in FEniCS?
Yeah. So Dr. Rishikesh is expert. I mean, Rishikesh's entire thesis is based on solving the fracture mechanics using something known as phase field method, and he is extensively worked on FEniCS as well. Yes, answer to that question, yes, you can solve it. And if probably Rishikesh want to chime in and probably give more insight if you wish to.
Yeah,
Rishikesh?
hi, good evening. Yes, answer to that question is yes. Either in a discrete way or in a diffuse way, we can solve fracture problems. For the fracture problems, I think you are interested in K1 and K2. So we can calculate K1 and K2 if you are using as a discrete approach. But if you are going from a diffuse approach, it is relatively very easy. We are not going to calculate K1 and K2. So it is very easy to grow the crack also. So entire fracture process can be implemented in FEniCS. Yeah.
Next question. Can you comment on the capabilities of how is FEniCS compatible with meshing output from abacus and hypermesh?
How is FEniCS compatible with?
Meshing output from abacus and hypermesh.
Yeah, see, I have not actually, I don't remember taking the abacus mesh and using, as an input to the FEniCS, but I have seen somewhere online people doing it. Probably Rishikesh, if he knows, he can answer.
Yeah, we can convert actually .inp to the readable file. But thing is, we need to use some other things. Mesh.io. Mesh.io is the way we can do that. But we have we have faced some issue. It is not that easy. But yeah, of course we can do that. But we are going to show you very simple way, GUIGMS, where we can get our meshing done. But I'm not sure about other platform like hypermesh. But I know we can convert our .inp to readable file in FEniCS.
Yeah, just to add up to Rishikesh answer, say the way I understand, hypermesh is a dedicated mesh software, so it should be able to give some MSH format or something which can be converted so that FEniCS can read it. Again, that's my guess. I haven't worked on it. I hope that answers your question.
Yeah. Next question. Can you please comment on the capabilities of FEniCS as compared to other FEM source codes such as Deal2, CalculiX, Almer?
Yeah. So Deal2, yes, I think I have answered that question. CalculiX is the way I understand is more of equivalent to abacus. So you can't really write the things in variational forms. So that's where we have the advantage in FEniCS. The third one I haven't heard of before. What is that software?
Almer.
I don't know.
Yeah, I don't have any experience with Almer. So.
Okay. Yeah. Next question. How much time does it take for a person who is working in ANSYS or abacus to change into FEniCS?
Yeah, so I mean, yeah, excellent question. Thank you for that. Say, it depends. What is your background? If you have done some basic FEM course, UG level or just even a PG level FEM course where you are aware of strong form, weak forms, these things. As far as the rudimentary problems, small strain, elasticity.
Hello, your voice is cut off.
Hello, are you able to hear me now?
Yes. Can you repeat your answer?
Yeah. So thanks for the question. Yeah. So it depends on your background. If you have done basic FEM course where they teach you mathematically preliminaries of FEM, the strong forms, the weak forms, and everything. In that case, it doesn't take not even more than a day. And if you are a bit aware of, the Python and everything, and if you are well versed with weak forms and strong forms, at least for the rudimentary simple problems, like your elasticity, linear one-dimensional problems, so stationary problems, kind of things, it shouldn't take more than 4 to 5 hours. I think the learning outcomes at the end of this workshop, you'll be able to do at least 2D to 3D transient problem, and as well as small strain elasticity problems, Poisson's equations, sort of things. So just hold on for a couple of more hours. That will answer your question more comprehensively.
Yeah, I think we should proceed and we'll have a question answer session.
Yeah, before proceeding to that, I have seen one question which is very relevant now. Yeah. How active is the user forum? Yeah, user forum is very active, and you can get answer in one or 2 days. But thing is, you have to ask your question in a very nice way. you have to provide your minimal working code so that they can debug and then give you the answer. Yeah, this group is really active, and I think there is a dedicated conference and a workshop every year. So I think this group is really active.
Yeah, so just to add to Rishikesh this response, there is a references in, we are providing the link for FEniCS discussion answer question answer discussion forum, or you can Google it as well. As he said, it's a very active forum.
Yeah.
Akhil, anything else?
There are some other questions, but should we proceed with the presentation?
No, we can take the questions, no issues. I mean, entire next 2 years, 2 hours will be dedicating to demos. We can take the questions, no issues.
Yeah, can you comment on the vibroacoustic simulation capabilities between FEniCS and abacus?
Okay.
Vibroacoustics.
Honestly, I don't know. I have not worked on the vibroacoustics. I don't know the governing equations or anything. So sorry, I can't answer your questions. But probably Rishikesh might, because Shaima might be working.
Yeah, I know. I don't have any experience with vibroacoustic, so I cannot answer. But thing is, as we know your weak form, I think we can solve that. Only thing it can take is your triangular elements, and it can write your FEM weak form, and then we can do that. But I'm not sure if you are going to use some high order things, then we need to check. But as long as we are trying with the FEM, we can do that.
Yeah. Is it possible to calculate electrical properties like electrical conductivity, shielding parameter with FEniCS?
Thanks for the question, but I think we need more details or more precise questions. I mean, from what? You want the electrical properties, shielding properties from what? I mean, see the bigger FEniCS solves, it's for dedicated for FEM, solving the PDEs and giving you the solutions. If you can fit getting the properties, let's say some sort of homogenization are you doing or something, or multi-scale problem, I think that would be more precise question. So without much details, I can't answer this question.
Can we couple subroutines written in Fortran with FEniCS?
As far as I know, no, you can't couple the subroutines written in Fortran with the FEniCS. Rishikesh?
Yeah, it says that we can do that, but I have tried, it was not working. Yeah, so I can say it is not working, so we cannot couple that.
Okay.
But so somewhere we will see. I have seen we can do that, but I have tried that. It was not working.
Okay.
I think the other questions can be answered as we proceed because
Okay. Thank you, Akhil.
So some of the questions are a bit okay. So we have many questions now, but as long as we proceed, it will be answered automatically.
Yeah. So yeah, these are the tools. Dr. Rishikesh will be, helping you with the installation and the para views. We will be helping with both installation and doing the rudimentary things associated with the tools. Yeah. So now we are moving with the introduction. We'll be getting into the setting up the system. So initially, as far as experience goes, as for installation in Ubuntu, it wasn't a much difficult task. But if we had a Windows system at that time, or the cluster, we have had the problems. So most of us now, especially this is a time where we had Windows 7 or Windows 10. So now, now with the advent, Windows 10, there is something known as Linux app or something. With that, things were much easier. Here, I will give control to Rishikesh, so he will be able to talk much better.
Yeah, thank you, Pramod. I think can you stop sharing your screen so that I can share my screen?
Yeah, sure. Yeah, Rishikesh.
But I need this. Okay, so.
Yeah, bro, tell me.
Are you able to see my screen? Hello?
Yes, Rishikesh, we are able to see it.
Okay, so before proceeding that, this is I want to show something regarding the FEniCS. So this is the FEniCS group where we can post our questions. So here they write everything. So we need to write your question precisely, something like this. and then we need to provide your minimum working code, something like this, so that they will be able to answer your questions. Okay. So I'm going to help you with the installation stuff. So if you have Ubuntu system, so installation is very easy. Just we need to run these 4 commands in our terminal. But what if you have a Windows system? So now I have Windows 10 system. You can install Ubuntu app, which is similar to this. Okay, so now you have terminal. So this is the Linux terminal. You can use use these commands to install FEniCS. So now I will show you where it will be after installing. Actually, I have already installed. So after installing, you can go to this directory, and then you will see the demo. The demo is located here. So there are 2 parts within the demo. So you can see here. So here documented and undocumented. So documented is trusted one. So you can trust and you can do whatever you want to do. So here we have many documented demo. Okay, so this is the installation of FEniCS that we can see here, and just we need to run these commands using this terminal, and this is similar to our Ubuntu terminal. So before proceeding to the other sections, in FEniCS we need discretization of the system, and as we already told, for the discretization we are going to get help from GUIGMS. So GUIGMS also you can install using the terminal, and these are the commands to install the GUIGMS. So GUIGMS in Ubuntu. So these 2 commands, after running these 2 commands, we will be able to install GUIGMS. And for the post-processing, we are going to use ParaView. So ParaView installation is also a bit easy in Ubuntu. So this is the command you can use to install ParaView in Ubuntu. So after installing this Ubuntu app within your Windows 10 system, you will be able to control everything. So okay, so I will now explain how to generate discretized system using GUIGMS for a very simple geometry. So by using this command, you can open your GUI, GUIGMS GUI. So are you able to see this GUIGMS GUI?
Yes.
Okay, so how GUIGMS works? So thing is, we need to give all the data points. From the data point, we need to construct a line, and then from the line, we need to construct a surface for 2D and 3D. Yeah, so I will repeat this. So this is the command GUIGMS, and this is your file which you are going to open here. Okay, so first we have to give all the data points. So here I'm constructing a very simple shape. let's say, for example, I am constructing a rectangle. So to construct the rectangle, first we need to give 4 points. And for the regarding the geometry discretization, we can control the discretization using this LC parameter. So as of now, I am just keeping LC parameter 0.1.
Hello, Ishkesh, 1 second, 1 minute. Yeah, there was one question regarding from where we can install Ubuntu app, any trusted source.
No, just we need to
Just through terminal,
type here.
right? Can you show
Yeah.
that once?
No, for Ubuntu app installation, we can go here.
Yes.
Okay. Type Ubuntu, then it will show Ubuntu is not there in your system. Okay. It is within Windows 10. So after that, you can click that and you can install.
Okay. From where are you downloading this Ubuntu app? That is the question, I think.
Yeah, it is within the Windows 10.
Okay, it's Windows Store
It's,
itself. Huh?
yeah, Windows Store. Yes, it is just an app which we use.
Okay, okay. I think that's all.
Yeah, to install any program. Yeah.
Thanks.
Okay, so now we can give some data points. So let's say, for example, I'm going to construct a rectangle of size 1 and the starting point is 0. So LC parameter is just to control the discretization. Yeah, so as I said, first we need to give all the data points. So after giving the data points, we need to construct a line. So after constructing this line, we can assign to this domain as a surface. To do that, we can take this plane surface, and then here we can say we can see this command: press E to in selection and Q to abort. So here we after selection of this domain, we can press E command for the selection. So now we have assigned domain with a surface, and now I think we can do the meshing. So after doing this, you will be able to generate triangular elements. So one of the limitation I see in FEniCS is it is very good for triangular elements, and the group is now working for quad elements. So yeah, this is the one limitation I have faced during my research and during my experience with FEniCS. So, but in GUIGMS, we can easily generate quad elements. To do that, we need to go to transfine. So here we need to define how many division you want on this line. So this is the division. We can do this. So for example, I'm doing here 10 by 10 by 10. So after selecting all, we need to press E for the in selection. So now we have given that. So now we have to transfine the surface. We can select the surface and do this. After doing this, we need to recombine the transfine surface with the existing one. And that we can do by clicking this. And then once you done with the process, you'll be able to see this.
Hello, Rishikesh. There was a question in WSL register distribution failed error coming in Ubuntu command prompt.
What is that?
WSL register distribution failed error.
Oh, is he using Ubuntu or Windows?
Akshay, can you raise your hand, ask your, and then I'll unmute you. You can ask your question.
Hello, Akshay. Hello. I think.
Ashwin, can you raise your hand?
Am I audible?
Yeah.
Sir, actually, I have a
Gautam,
question regarding meshing.
Gautam,
Yeah.
can you
Which
wait
machine
once?
you are using, Ubuntu or Windows?
Sir, I'm not the guy who asked the question.
Yeah, so
Okay.
Gautam, can
I
you
have a
wait
different
once?
question.
First we'll get with Akshay's question.
Hello. Yeah, Gautam, you can ask your question.
So, Rishikesh, now Akshay is asking his question.
Oh, okay.
Hello.
Yeah, Akshay. Yeah.
Yes, sir. Yes, sir. I'm using Windows 10 right now, sir.
So after installing your app, are you getting any error?
Yes, sir. I installed the Ubuntu 18.0 for LTS, but
Okay.
after installing it's showing WSL register distribution failed with error.
Okay. So I think you have some bigger issue. So I think you have to start with admin, something like that. I think we have fixed that. So, yeah, this issue will come, but thing is we need to check in internet how to fix this issue. Yeah, I think you can fix this issue by looking into internet.
Okay, sir. I will try, or I will mail you any.
Yeah. If you have any question, and you can send me an email.
Sir, thank you, sir.
Hello?
Yeah.
Yeah, yes, Gautam, you can ask your question.
Sir, I have a question regarding the meshing. So, basically, I am familiar with finite element method, and I wanted to understand that there were a lot of options in that. So, get a better understanding of meshing, sir. What are the prerequisites that we need to understand for designing the mesh?
Actually, for designing the mesh, we need to first see where the gradient is. But a priori, we don't know where the gradient is. Okay, so for the better approximation, we need better mesh.
Sir, I'm talking about what are the prerequisite concepts that we need to have in mind before we are designing a mesh. Sir, I'm talking about the topics that we should refer before meshing.
No, before meshing, we don't know where the gradient is, right? So for the designing process of the mesh, first of all, we should have some understanding of the gradient of the solution. So if you have more gradient, so we need to place more number of elements within the gradient field. Okay, so I think for the first starting, we should start with the structured mesh.
Okay.
Okay, so this
Rishikesh, there is one more question from Sharath.
Okay.
Hello.
Sharath, you can ask
Sharath.
your question.
This is Sharath. So I have a couple of questions, Rikesh. Actually, one is about the WSL. So I think when you need to install Ubuntu as an app in Windows subsystem, we need to go for go into developer mode. Until unless we go to developer mode in Windows, we cannot install Windows subsystem like Linux, like Ubuntu. That's the answer for one Akshay's question.
Okay. Yeah. Somehow I have fixed that, so I don't remember. Yeah. Good.
Yeah.
Thank you.
Secondly, I have a question about GMesh. Generally, couple of years before I tried to use GMesh, but problem with that is that every 3 months I will get a new update in the GMesh. So you're sticking to 3.08 or something, and then now if you see GMesh website, it's in 4th generation. So how you are actually sticking to one module of GMesh and going ahead? So how things are going on?
Yeah. So thing is, till now we don't have any issue with the FEniCS reading file. Only the problem will be if you write your own routine, let's say for the reading the text in MATLAB, we need node and element connectivity. we should have some issue with the reading. So that's what I have faced issue. But as long as FEniCS are concerned, we don't have any issue with the older version and newer version.
Okay, if you agree, I have another question. Like, I'm working on composite materials. So what happens is that in abacus, we have a separate module for composite materials and so on. But when we go for a open source modules like FEniCS or Elmer or Deal2, whatever it may be, so for the orthotropy properties of a material can't be inherited in these modules. So is there any possibility of using more than 2 properties in FEniCS right now?
Yeah. I will tell you. I will show you today to
you.
use more than 2 properties.
Yeah,
but regarding to that orthotropic, these things we need to write it. So that thing will be embedded in your D matrix. That we will see how we can.
Thank you.
Regarding the 2 material system, I was just going to show that how we can take care.
Thank you.
Yeah. Okay, so as he has asked the question, I will show you how we can take care of the 2 domain system. So this is the 2 domain system I have already created. So starting point for this is 0.000 and domain is 1x1. And I assume I have a property of steel here and a property of aluminum here. And I have subdivided my domain into 2. Okay, so here we can partition the system within the GUIGMS itself. To show you how we can do that, we can see the so basically we have created 2 surfaces that I have already shown you. That first surface is less than 0.5 and other surface is more than 0.5. This one. So this is my first surface. This is my second surface. So that I have assigned here. And then regarding we can have different boundary conditions also in FEniCS. So I have assigned different line as a separate grouping. So here I have assigned 1, 2, 3, something like that. So that we can see here, I have assigned different numbers to the physical lines. The command to assign that is, if you have to assign surface, we can assign using physical surface. And if you have to assign line, then you can assign using physical line. And once you, so this is the way to create 2 surfaces, 2 domains. And once you use this command called Dolphin Convert, it will create you a readable file for the FEniCS. So a readable file for the FEniCS is .xml. So let's so I will show you the command how you can do that. So first you need to save this .guo file to .msh file. So this is the way we can do that. So I will create 2D system. So 2D discretization. Then we can save. So this saving will be in .msh file like this. As I have already done, so it will pop up if you want to replace it. Okay, so I have already created. So now we can use this command, Dolphin Convert, and then bimet.msh, and then bimet.xml. Okay, so after doing this, you will be able to see 3 files, naming, actually we have 4 files. First is msh that we have saved. And then we have bimet.xml that we have given name. And then in addition to that, we have 2 more files, which is one is bimet facet and another is bimet physical. Okay, so bimet facet will have how many domain we have created and the index associated to that. And bimet physical will have bimet physical will have index associated to the material, and facet will have the boundary. So how we can read that I will show you in FEniCS. So we can use ideal for the editor tool. So this is my simple ideal editor tool. So here I have written, first we need to call FEniCS. So this is the way we can call from Dolphin import star. So it will load all the Dolphin routines, and this is for the plotting that we can ignore as of now. Pramod will explain in detail. So how we can load the mesh which we have already generated using Dolphin Convert command. So this is the key. We can use this key to load the mesh. So this is the folder where I have this BIMET created file, .xml file, and then material. So for the material, I already told you the index will be associated within the physical, and for the boundary, index will be associated within the facet. And we need to write a simple user expressions. So it will assign, if we have index 1, then it will go to material 1. If index is 2, material will go to, so material will be our second material. So this is the simple subroutine that I have written. And so for the BIMET, I have assumed these two property. So, and here we can just call our user subroutine. So this is the subroutine I'm calling here and assigning our different material property. So this is the E and U that we have assigned already. And we can see how it is, see the variable using this .pvd. Pramod is going to explain you in detail. And if you want to see the material and boundary index that we can see in paraview. So this is the output file for the paraview that we can write using file command and .pvd mode. So I will show you the index for the boundary and material. So if you have installed paraview within your system, so this is the command paraview. So I have already assigned material index to my domain. So this is the material definition. So here I have assigned 70 E3, and here I have assigned 210 E3 E. So this is for the E, and the index associated with the material and boundary we can see here. Okay, so if you can see here, the index is 1 for the material 1, and index, so this is the thing, index is 1 for this side, and another surface index is 2. And for the boundary, we can see here. So we have different number for the different boundaries. And how we can assign within the FEniCS, I'm going to just show you in brief. Pramod will explain you in detail. So this is the way we can assign. So let's say, for example, I have elasticity problem. So these are the definition, we can do that. And for assigning the boundary, we can just call the boundary and which index. So for me, for the left side, index is 8. So I have assigned 8 for the left side. And for boundary right, we have index 5. So here, if you can see, I have assigned, I have applied constant displacement on the right surface, and fixed UX and UI on the left edge. So if you run this simulation, I'm not explaining everything in detail now. So Pramod will explain. So this is the result we will get. Horizontal displacement, as we have applied 0 UX on the left face, 0, and on the right we have applied 0.01. So this is the way we can call. So this is the stresses, I think. Yeah. Yeah, this is all about how we can apply boundary condition from GUIGMS created mesh. So we can also define boundary condition within FEniCS itself. Just we need to write simple definition or simple class file. We can do that. Yeah. So answer to that
Hello,
question.
Rishikesh. There was a question. How can you specify boundaries if it has regular shape?
Yeah. So if you have irregular shape, so if you have defined your irregular shape within GUIGMS, so we can assign index here. Let's say, for example, I have created my domain using a spline. Let's say for this is spline 1, and this is spline 1, this is spline 2, and this is spline 3. So we can assign index associated to that, and then we can read the same index within FEniCS like this. Yeah. So like this. So just we need that index which we have already assigned using GUIGMS. Yeah.
Also, is the one more question is there? Is the GMesh, it is similar to ANSYS mechanical APDL as to create points, lines, area?
Yeah, it is similar, but I don't know which format ANSYS gives. Somehow we need .xml file or .msh file. If we have .msh file, we can easily convert to a readable file for the FEniCS. But concept is same. So concept is first you have to throw the points which you want. Then from the point we need to construct line. Then from the line we need to construct surface. And if you have 3D, then you have to construct 3D surface and volume.
I think that's the question for now. You can continue. Thanks.
Yeah. So as I have already explained, one of the difficulty with FEniCS is it can, as of now, it can handle triangular elements. So just we need to bother about triangular elements, but as I have explained, we can generate quad elements also within GUIGMS. Yeah, as of now, this is it. Pramod, can you now explain in detail about the FEniCS routines, which you are going to explain?
Yeah, thank you very much, Rishikesh. Yeah, so to summarize, for FEniCS, we need input as a sort of mesh or a domain information that we can either use it. Just a minute, let me share the screen. Yeah, so that we can use it. We can get that from either the inbuilt Mesh.io software, which has the primitive shapes in place. But other than that, if we needed really complicated, as someone was asking, splines and everything, then one of the resort was to GMesh. From there, we can convert the meshes from MSH to Dolphin readable format. That is what Rishikesh showed. Yeah. So with that, and then
GMS and in GMS, sorry, Pramod, in GMS we can create very complicated geometry. So I have just shown you a very simple example, but we can do very complicated geometry. Okay, can we create composite? Yeah. So yeah, we can create this one. So just I will show you one example here. I was about to show it maybe, but I have forgot. Just a second. We can create that.
Yeah, Rishikesh, you may want to share your screen.
Okay, sorry. Yeah. Okay, let's say for example here I have plate with a hole, but for the composite system we need to have a material here. So that we can do. So just I'm assigning the surface. And then I will assign surface for this domain also. So now we have 1, 2, 3, 4, 5 domains. So like I have already said, we can group this as a physical surface. So now we have to group this as a physical surface for so here we can create a triangular shape. So here we have a triangular shape here. And now we don't have any hole. So now we have a different system. So now we can save this. And then we can group by writing physical surface. Yeah, that's what we can do, and it is very easy. Do you want me to show here how to define how to do physical surface? Yeah, it's fine. Yeah. Any question now? Okay, so is it possible to demonstrate crack growth in mode 1? Yeah. So we have code, but it will take some time. I can just show ParaView files which I have now, as of now, which we have done for done using phase field, not as a discrete way, but we have done with the diffuse approach. So let's say, for example, we have a crack, and then we have applied phase shield model to grow the crack. So let's see how it is going to grow. So it is a bit slow. Let's say I will show you after some time. Yeah, so see, crack is now growing. But this is not for the tension test. This is for the shear test. But demonstration is that we need to explain many things. So I think demonstration is not possible. Maybe Pramod can say. Pramod, are we going to explain
no,
crack growth?
I mean, see, because for that we might need to explain the phase field and everything.
Yeah.
Yeah, and then the difference between phase field and diffuse approach, Rishikesh will be able to answer that.
Yeah, so but it is very easy to take care. So that's what I have explained. I have shown here. It is not that difficult to do this.
Yeah, Rishikesh, there is another question. Difference between phase field and diffuse approach.
Yeah, phase field and diffuse approach both are same. There is no difference actually.
Yeah.
Okay, so Pramod, now you can explain the demo.
Yeah.
If you don't have if they don't have any question, I think.
So yes, to summarize it, if we need a complicated mesh, we can use a GMesh that can be readable in the Python code of FEniCS. Once we read it, then we need to impose the boundary conditions. We need to write the weak form of the governing equation, or the variational form as we will like to call it. Impose the boundary condition, solve it, and then if necessary post-process compute the other secondary variables such as stresses and everything, and then we can output those in ParaView. The file format that ParaView takes is of PVD and VTU. PVD is so both are essentially sort of, you can open in Notepad++ or text format, and then you can read those files. You need to write in a particular format but that FEniCS takes care by itself. PVD consists of the time series of the VTU files. If you observe the one Rishikesh, the animation played at the top, you might be able to see the numbers were moving. I mean, the frames were moving. So he had loaded the PVD file. There contains for each and every time which VTU file to load, and then that's how he was showing the crack propagation in the shear case. Yeah, so that is the gist. So for the coming back to the major focus for the FEniCS, all you need is a variational form. The input can be mesh that can come either from the inbuilt preliminary primitive shapes using mesh IO, or you can use a bit sophisticated softwares for much more nuanced examples such as GMesh, and then in the end you can post process in the ParaView. So this is a flow. So the mesh input to the FEniCS Python code. So FEniCS, just to reiterate again, FEniCS is just one of the libraries, such as you might have heard of NumPy, SciPy. FEniCS is one such library. That FEniCS dependencies is based on Dolphin, Fiat, FFC, and those sort of. And the output can be visualized either with a matplotlib or in a much better way in the ParaView. So these are all three separate softwares in themselves. They are ocean in themselves, but we'll be just giving you the brief overview so that you can get started with your things. Yeah. So with that, so shall we proceed with some example, Rishikesh? Hello.
Yes.
Yeah.
Yes. But just one addition. If you have very simple geometry, let's say for example, you need a square, so we can create using FEniCS also. But complicated geometry is a bit difficult, so we need to use GMS. That's what we have. That's why we have shown how we can generate using GMS. So very simple example we can create using FEniCS also. Maybe Pramod will say.
Yeah. Yeah. Thank you. So can we import .step or .igas CAD file? I haven't imported, Rishikesh.
I think we can import to GMS, and then from the GMS we can save to .msh, and then .msh we can convert to .xml.
Yeah. So we'll move ahead with the presentation. Yeah, so I hope now the installation. Yeah, so I kindly request you install in your local system right now, so that probably we can move ahead, and then when we go ahead further, you can code along with me, and then you can get the hang of what exactly is happening and everything, right? So yeah, in that case, if you need it, you can probably take a screenshot of this slide or something, and then parallel you can probably install as Rishikesh explained. Yeah.
Pramod, there was a question. Can we import stop or IGS CAD step .step or .igs CAD files to FEniCS?
Yeah, so as Rishikesh answered that, so we can directly we can't. So, but you can import that .step and .igs into GMesh, and then convert using the GMesh the .step and .igs format into the MSH format, and then using the Dolphin Convert command, you can convert that MSH into an XML, which you can load into FEniCS. So, just to reiterate Rishikesh's answer.
Yeah, Gautam. Actually, we have already shared a PDF file on the website, I think, for the installation stuff.
Yes.
Can you go there? No, not here. Yeah, FEniCS workshop. Yeah, I think we have shared already, so we can.
So nonetheless, I'll paste the link in the chat box so that.
Yeah, it will be easy for them. Yeah, thank you, Pramod.
Yeah. So yeah, using these commands, probably you'll be able to install as far as the Ubuntu goes. You may be able to install the things. Okay. Else, nonetheless, you can Google as well. I mean, and in that case, it's just a pretty straightforward to install. Yeah. Thank you. So shall I proceed?
We'll start with demo.
Yeah. Yeah. So before just getting into demo, just one last slide probably. So most of the codes whichever we are showing, as I said, we'll be coding in Python. So depending on your Ubuntu version, either you might want to invoke the Python, it might be by default Python 2.7 or Python 3. It depends on your Ubuntu version. So it's essentially a Python code where you'll be loading the geometry, you'll be identifying the domain, and then you have your own PDEs in mind, you have your own boundary conditions. Convert that PDE into the FE variational problem. Here we assume that you know how to convert the PDE into the strong form, the governing equation, and accompanied with the boundary conditions into the weak form. And then we are assuming that you know that. Nonetheless, we will be providing just a very cursory overview of it. And then that FE variational problem, you have to code it in Python. So the same thing, you have to load the domain. So that's a mesh along with the variational problem, the boundary conditions. Then those boundary conditions will be imposed, and then you need to solve it. And if necessary, you can use post-processing to compute the secondary variables like stresses based on your primary variables, the gradients of strains, and all those kind of things. And then if necessary, you can dump into VTU format or the VTU format and the PVD format, so that you can have the visualization and further post-processing in Paravi. So yeah, this is how the overall code, the syntax of the code more or less looks like. So just to give you, so this is what the simple code is. Okay, this around 15 to 20 lines of code. It solves the 1D Poisson's equations, which we'll see in detail. So firstly, we are just loading the necessary things. If you are familiar with the Python, you know how to load the numpys and scipys. In the same way, we are loading something known as Dolphin, and then we are creating the mesh. So this is what Rishikesh was talking about. Either we can create a simplistic mesh using the inbuilt functions such as unit square mesh, or we can use the GMesh and then convert the MSH format into XML and then load it appropriately, and then apply the boundary conditions, and then you create this is a variational form. This is what necessary things for defining the variational problems, and we are computing the solutions, and then followed by we are dumping for a Paravi visualized format. Some of the things, preliminary things, you can see it using matplotlib as well, the very famous visualization block of Python, and then you can see those. So this is how the code more or looks in every case. These are what the blocks look like. There will be few changes. You'll be either loading from GMesh in first case, and variational problem you might need to define much more extensively, and then solving either for the nonlinear case you need to invoke the Newton-Raphson, and then instead of Paravi alone, you just might very well be satisfied with just a matplotlib. So this is what the overview looks like. Yeah, so as I said, we'll just briefly see how the strong form can be converted into the weak form. So which is essentially which is also known as variational framework, and that we'll be coding in Python. So given, let's say you have some equations, del square u equal to f, just multiply with something known as v, which is a test function on through the entire equation, and then integration by parts. So this coming from this stage to this stage has two steps. One is integration by part, and second Gauss divergence theorem. So Gauss divergence theorem converts your the domain entire volume integral into the surface integral in the case of 3D, and then substitute back these, and then just impose the boundary condition attraction or the Dirichlet boundary condition. Yeah, so that's all. So the first example which we'll be looking at, this is a Poisson's equation. So we will have break around 5:30 or something. So this is already 5:24. So before that, before jumping into, so the next we will be just talking about the examples. We'll be giving you the demos. We will be sharing those codes so that you can download and you can start coding along with us. And then our commentary will probably help you with, okay, what exactly is happening in detail. So before moving into the next session, if you have any questions, you can ask based on the previous stuff.
Okay, so this,
yeah.
Pramod,
yeah.
Sorry, this Poisson equation is there in demo. So if you want to look now also, you can look into the Poisson demo Poisson. So it is there.
Yeah. So so most of the examples which we are seeing here are the very preliminary and help to beginners. Most of those codes are available, and even more sophisticated nonlinear codes, hyperelasticity, sort of all those codes are available in the official demo website of the FEniCS. The links which we will be sharing in the end are the references, should have those. If you want, I can share you in a FEniCS chat group as well. Just a minute.
And same thing will be there in your local directory where we have installed. Yeah.
Hello, Pramod.
Yeah. Tell me.
This is Sharad. So I have only one question that, the restriction with FEniCS is that it can only go handle triangular elements or tetrahedral. If you see 3D, it may be tetrahedral element. Am I right?
Yes.
Yeah.
Yes. As of now, yes.
Yeah. Are they first order or can we go for a higher order elements?
Yes, you can go for higher orders. That we'll see how to go ahead with higher orders. Yeah. Can we get the PPT slides? We are willing to share. We'll just ask Professor Ratnkumar, and I think we'll be able to share it. No issues about it.
Anyway, the video is already will be shared actually. The recording
Yes.
will be shared.
Yeah. So any other questions? See, the links we have pasted. One is for installation. You just open that PDF, and then you should be able to follow the installation. And the installation, you should be able to do it in a jiffy. Followed by the demo, just to have a look at what kind of demos are there. Out of those few of the demos, we will be doing it in the subsequent next session after the break. Other than that, if you have any questions regarding the overview skeleton of FEniCS, you can ask. We are welcome to take those. Minimum system requirement for FEniCS. I think that will be mentioned somewhere in the documentation, but I don't think even a minimal 4 GB system should be able to handle it.
Yeah, I was able to run with my old laptop. So I think we don't have any issue with but you will not be able to run complicated or computational expensive simulations. But for the simple, we can do that. No, Windows 10 is not essential. We can do using Ubuntu also.
Yeah, so we can do it on Ubuntu if you have Ubuntu. If you have Windows 7 or something, if you see the website phoenixproject.org, they provide some other alternative way through Docker. I have not tried it, but I think it should be possible. Yeah. So Akhil, what is the scheme? I mean, for how long is the break and everything?
Should we have it for 5-10 minutes?
I don't know. I mean, did Sir tell you something?
No.
Can you call him and ask?
Yes.
So f equal to Dirac delta function, will it be able to solve? Yes, it will be able to solve. Manish, answer to your question. Yeah, so this is a book link. Okay, this acts most of the whatever we are telling will be there in this book. So you might, and these are open source books. So you might want to download and and the read is pretty quick. You can finish it like a novel, probably in the span of 4 to 5 hours, at least to get started with elasticity, scalar problem, vector problem. Can we have homogenization in demo? I don't know. I'm not so well versed in homogenization. So, Rishikesh?
Pramod, can we share that link also? Homogenization problem is there. Maybe he can have a look.
Jeremy Blair link is what you are referring to?
Comment, yeah. maybe you can share that link. Maybe he will have a look.
Yeah, so this is one of the links where people are doing contact plasticity and so those advanced stuff, and so you might want to have a look at it. Linear thermoelasticity, multiphysics. So just explore these. It's a very vast support is given to this.
Hello, Pramod.
Yeah, Akhil.
We can take a break for 10 minutes.
Yeah.
The candidates can leave and then join back in 10 minutes.
Yeah, fine.
Before that, there is a question from Gautam.
Yeah.
Gautam, can you unmute yourself?
Yes, you can use Ubuntu 20.04 LTS.
Gautam, you can ask your question.
Actually, it was pressed by mistake. Sorry.
Pramod, can you answer to this question? I'm not sure what he's asking.
Which
The
one?
installation does not seem straightforward in Arc.
Yeah, see the Arch, I think is probably, is it a Red Hat Enterprise Linux or something, Jacob? So I don't know. I mean, I have never used on those platforms. See, the platforms I used are is only Ubuntu. So Rishikesh is used probably the Windows and Ubuntu. Other than that, yeah. So I don't know what is Arch. Sorry, I don't know answer to that question.
And even it is not straightforward in Hull, right?
Yeah, in the cluster also we have had troubles, our own share of troubles. Yes, so it wasn't the cluster was based on CentOS or Red Hat Enterprise, RHEL, Red Hat Enterprise. So we had our own troubles. Yeah. Other than Ubuntu, Windows being an open source, it wasn't so straightforward. And so is the case with Abacus, right? Abacus is not directly, easily installable in Ubuntu. Oh, okay. Jevin, is that a question? I suppose that's an answer to Jacob's question. Yeah, so guys, we can join back at 5:40. We'll start again the demos at 5:40.
Can anyone open directly, Pramod?
Yeah, Rishikesh, what?
Can anyone open directly that we don't need any password?
No, we don't need any password. They can view it, they can download it, and they may not be able to modify it.
Okay.
Yeah, so Akhil, shall we start or shall we wait for some 5 minutes or more?
Meanwhile, if anybody has question, they can ask.
Yeah.
I think we should wait for 5 more minutes.
Okay.
Yes, yes. Yeah, let's wait. And if anyone has any questions, you can raise your hand or you can just post it in the chat. Hello, Paras, you can ask your question.
Yeah. So a question to Rishikesh. I already tried to ask this, but probably it was not considered. So could you please comment about your modeling of discrete cracks, say as an XFEM or something? Like I could not find any example in this Comet collection or something.
So XFEM, we have not tried. I think it is not possible also. Yeah.
It's not possible to do XFEM with FEniCS.
Yeah, because so in XFEM we have enrichment functions, but here we have standard elements. So I'm not sure how we can add enrichment functions within your approximation space. So XFEM, I think nobody has done it also. Mostly I have not seen.
Okay. Okay. Thank you.
Hello. Yeah, so coming 3 days will not, they will not be on FEniCS. So how to start working in FEniCS? Can you list the prerequisites?
Sir, this was my question.
Gautam, is it Gautam or Adarsh?
Sir, Gautam.
Yeah. So yeah, the book I have shared, right? So that's just a very quick read. You can probably start with that book, and that's just around 150 lines book, but most of them you can finish it probably within 2-3 hours or so. So it shouldn't be a problem. I would suggest you start with that book, right?
Okay. Sir, one more question that, sir, like in this, we are using 2-3 softwares like ParaView, that meshing software and all.
Yes.
So, sir, wouldn't it be kind of difficult for bookkeeping, something like that?
No, not necessarily. The reason it's not difficult is because the crux is a FEniCS here. The GMesh and ParaView are just supplementary. Though just augment your understanding. Just that's all. You can very well get rid of GMesh. Okay, you can at least the primitive shapes you can do it in FEniCS itself. And the ParaView also you don't need. You can do the plotting with Matplotlib itself. But if you want to save the data and later on just visualize it for that purpose the parallel, so it shouldn't be that difficult bookkeeping.
I
think we should start, Pramod.
Yes.
Yeah. So yeah, welcome back everyone. So just a minute. So yeah, welcome back again to this next session. firstly, we will be seeing the Poisson's equation as an example. The codes which we are going to do has already been provided to you through the link I have shared through Gmail Drive. You may want to download those. In the meanwhile, I'll start coding, and start providing the commentary to you, so that things will be much more easier, so that you'll be able to understand what exactly is happening on each line, and then you'll be able to appreciate it really well. Okay. So in the case, just for the completeness, I think I shared the code, the drive.google.com. You might want to refer to your chat here. Yeah. So coming back to the slide, yes, the first Poisson's equations. So the equation in its canonical form is minus del square u equal to f, defined in omega domain. This is domain of your interest. It can be a square plate, circular shape, or something. But here we are only choosing the simple ones. The complicated, one of the most complicated example is already shown, the bimaterial by Rishikesh to you. So I will not be covering that. Then the imposition of Dirichlet boundary condition. So on something known as gamma d, the boundary with a subscript d, Dirichlet boundary condition, and then del u dot n equal to g on Neumann boundary condition. So these three are your equations, along with two of the boundary conditions. The first equation. This equation is generic. We haven't stated whether it's in 1D or 2D. But initially, we probably will solve the 1D equation, and then we extend it in higher dimensions, so that you will be appreciate. Doing it going from 1D to 2D, it's a lot easier, and 2D to 3D as well is an easier. Which initially someone asked regarding the fundamental core philosophy difference between MATLAB and FEniCS in terms of FEM. So doing the MATLAB in converting, going from 2D to 3D requires a lot more hard work. That may not be the case here, that we will be able to see. Once we write the variational form, we will be able to segregate them out as a bilinear and linear form, and then equate them. So the bilinear form will, at least for this equation and with the given set of boundary condition, the bilinear form will be of this form. A u comma v is a bilinear form. It's a bilinear because it's a linear in both test function and trial functions. U is a test function, your v is a trial function, and then your right hand side also, that's known as a linear form, is only the function of your test functions, where f is your source term, integrated over entire volume. Omega is the entire domain. Gamma is essentially entire domain minus one dimension. If it were a 3D, the surface becomes your boundary. If it is a 2D, your extreme ends become or edges become your surfaces. If it is a 1D problem, the points become your surfaces. Yeah, one of them asked the question whether the Dirac delta function can be incorporated as a source function. Yes, it can be, but we will not be seeing that example. Yeah, so this is what we are going to see. So this is your essentially A equal to L is in a variational form or a weak form, which comes a strong form to convert it into weak form, which we discussed before. So this is the equation. Sorry. Yeah. So this is how the code looks like. If you download the codes and if you open it, we have considered some form of f, which is given in the book as well. The same example we are considering. So this is how the code looks like. So firstly, I'll just give you again the overview, and then we'll go back to the code. So firstly, we are importing the Dolphin, just the way we import other. If you are familiar with the previous Python, if you have some experience in Python coding, you can import the NumPy or SciPy. So from Dolphin import star. Yeah. So one of the problem. Yeah. Let me just complete this one. Later on, we'll be creating the mesh. So this is a variable name we are assigning mesh. We are using the something function unit square mesh. It is an inbuilt in Dolphin. So as I said previously, the primitive can be loaded this way. If you want to come up with a circle, you can use a circle, comma, and some other argument. Those arguments, unnecessary arguments, you can search in documentation and see what all functions are available. So square, circle, rectangle as far as 2D goes, and for 3D goes, your sphere, your cube, cuboid, ellipse, ellipsoid sort of stuff. And then you have something known as now, yeah, this is a function space, right? What the case we are going to study is a 1D. So on that case, the problem, the unknown parameter is of scalar field, right? Here our interest of parameter u is a scalar field. Don't confuse this with a displacement yet. It's just a u. It can be a, a temperature, or it can be a concentration, for diffusion class of problems, temperature for heat class of problems. So this u is a scalar field. The first example is a scalar field and a linear equation, right? So this is how we are going to apply the Dirichlet boundary. So this is the boundary is a class or a function that is associated with a dolphin. This returns actually a Boolean. So the Boolean is either 1 or 0, right? So what it does is it goes through entire domain's boundary, and then whichever you want to associate it with a Dirichlet boundary condition, you can specify this one, and it will return those points as either 1 or 0. If it is a 1, it will treat it as a Dirichlet boundary. If it is 0, it will not impose any boundary condition on that. Okay, so the Dolphin EPS is a machine, the machine epsilon actually. See, computationally, you may not have always possible. 0 may not always be possible. But you can have some tolerance, the numerical error, round off error sort of things. So if I want, the less than 0 and greater than 1, that is how I am choosing it this way. And then the boundary conditions, I'm imposing the boundary condition. So the boundary condition at 0. So this is u0 constant 0, 0. And then the boundary condition imposed is using Dirichlet BC, is again a construct of the Dolphin itself. There the arguments goes as v, the function space which we are defining. What is the boundary condition value you want to specify? That is through u0. And then the third parameter is where you want to specify, that is given through the boundary, right? So yeah, these are the boundary conditions. So boundary condition I'm imposing on v, that is on the function space, that is on the variable u. The constant value is u0, which facet of the domains, which facet of the boundary, that is given by the boundary actually. So, and this is how we define, this is the crux of variational problem, variational function. So we define something known as a trial function. If you notice here the u is a trial function and our v is a test function. So yeah, so u, the trial function, we will be specifying. The v, the test function, the argument goes as whichever the function space. If it were a vector problem like our elasticity, where the unknowns are either 2D or 3D depending on the dimensionality of the problem, it would have been a vector function space, which we'll see in subsequent example. Yeah, so then u is trial function of v, test function of v. These are again the construct of the Dolphin itself, right? And then f we have considered. The purpose to consider this is to show that, okay, some complicated example can be considered. So here we are considering some arbitrary exponential to the power x minus 0.5 whole square and all those kind of stuff, right? So that is what our body force is. It's something like a gravity. In the case of gravity, we have the constant minus 9.81 acting in y direction. Here some complicated. Someone asked the moving heat source problem, right? Let's as of now forget about moving, but if you want some complicated heat source problem, yes, you can use it. So this is what one such example is. So here, so it acts as a sort of a heat source if it were a thermal problem. And then the G, the boundary condition is in terms of the G. So there are two boundary conditions, right? So one is the G stands for your Neumann boundary condition. So the expression for that is some sort of sinusoidal function. And your Dirichlet boundary condition, we have specified 0. So this is what your Dirichlet boundary condition is. Okay, so the Neumann boundary condition goes into the variational form. So we need to specify it that way. Whatever the Dirichlet boundary condition are there, that we will be specifying through Dirichlet boundary Dirichlet BC. Okay, so now we have defined the declared the variables. So this is what A stands for the bilinear form. So this is what so this inner product, right? So this is an integral omega inner product of the divergence or gradient of u, and then gradient of v, and then the integral over the entire volume, right? So this is how it reads. So this is how we are coding in Python this way, right? So the inner is again a construct of a dolphin. Inner grad of u. So inner grad of u we have taken, and we are doing an inner product with grad of v, right? And then the integral over entire volume. So that integral is defined by the star mark here, and the volume is denoted by dx, right? The dx is a variable or only reserved for the entire volume. If you want some sort of a surface, it is a ds, and if you want only on a particular surface, it can be ds, whichever the surface, as Rishikesh shown you the marking. If you are marked with, let's say, number 100, so you can say the ds in bracket the 100 or something. So this is a L. So this is a linear form. This is a the A is a bilinear, N is right hand side of the linear form, right? And then so this till this stage we have defined the domain, we have defined the boundary condition, we have defined the variational form, right? As simple as that. Followed by, so the unknown variable we want to compute it for u, which is a function of some v, again the function space. And then this is a command, okay? For a linear problem, this is how it works. Solve, and you want to equate this a equal to L. So that's our variational things, right? So solve a equal to L. So the equal to is just an one equal symbol is an assignment operator, and the equal to is an saying that a equal to M. Solve it for u in the presence of these boundary conditions, right? So it solves. After solving, I'm creating something known as Poisson.pvd in order, as I said, for paraview, for visualization. For basic things, you might ignore these, but let me complete it. So I'm opening the file Poisson.pvd, and in that I'm dumping, the process of assigning the solution to a particular file type is what I'm referring as a dumping. I'm dumping the u to the file. So you will have the folder file known as Poisson.pvd that will have the solution u, right? Or alternatively, you can plot the solution as well. So you are importing your matplotlib, the famous MATLAB Python's plotting functionality. One such functionality, matplotlib.pyplot as plt, and then we are plotting the u, and then we are showing it, right? So this is what the code looks like. Yeah, so if anyone has any questions, they can ask me. So if you don't have any question, we'll proceed, and I'll just code it.
Yes, some of the questions I have answered in chat only.
Okay, yeah. So if you have any other questions, you can. If not, I'll proceed with that, with the coding part. Yeah, so one of my friend asked me that how to run this this code, right? So you can if you copy this code or write the code in and save it as .py.
I will make show the running part.
Do you want to show running part?
Yeah, just
sure.
Maybe sure. Are you able to run in your system now?
I can by remotely connecting, but if you want, you can show it. I can stop.
Yeah, just I will show and you can explain. No, you can. Yeah, I will share the screen. You can explain.
Yeah, fine.
Also, there's a question: what solver does FEniCS use? So
FEniCS has, the Newton-Raphson also you can use, or some linear solver as well. There are other additional solvers also you can code. The advanced users can code those solvers, and then they can put into those repositories, and then you can use those solvers. By default, extensively we have used the linear and Newton-Raphson solver. And yes, you can tweak the parameters of Newton-Raphson, number of iterations and everything. You can control those.
Yeah. So are you able to see my screen?
Yes.
Yeah. So which one? Poisson.
Demo.poisson.
Yeah. So if you have Python 3 or say Python 3.7, then you need to use Python 3. Or if you have Python 2.7, you need to use Python. And then you can use demo Python, py, and then you can run. So let's see here. I don't have this. This is in just a second. Yeah. So this is the solution that Pramod has shown. So you can plot on the fly and you can save using this. But if you want to use ParaView for the post-processing, Pramod has already explained.
Yeah. So to answer Edwin's question, hi Edwin. So what is the typical time taken for simulation in FEniCS? I mean, it's a very wide question. It depends on your problem statement, what kind of equation are you solving, what is your domain size, what is your system configuration and all. But having said that, usually they take lesser than your molecular dynamic simulations. They may not be as long as EMD simulations.
Shall I open Python again, Pramod?
Yeah, Rishikesh. Yeah. So this is what, yeah. Fine. So, whatever the code we have shared, you can find those in either the book or even in the documentation, right? The links are mostly shared with you. Even if not, I'm sharing all this set of links with you. So in the chat box, you might want to save it in your local system and then you can refer back whenever you want. Some of them are question answer forum sessions. Some of them are related to book. Some of them are advanced lessons. So yeah, so these are the links, right? Yeah. You can find these all the codes and even better version or better documented, commented the codes in your documentation. Nonetheless, so for the sake of it, I'll be explaining each and every line as I've explained. So are all of you able to run the codes in your local systems?
Yeah, any of them.
Any of them, are you able to have followed the process of installation and then
yeah, just it will have good feeling for us.
Yeah, yeah. Anyone, any yes answer? I mean, no. If no, why not? I mean, is there any problem you are encountering? Yeah. So, have you installed YumShaf? Have you installed the FEniCS? Anyone? Could you run it? So, Sharat Chandramouli, how are you running the code? I mean, are you running with Python or Python 3?
Second, Pramod, I am asking MSHAF to MSHAF. You can unmute. You have unmuted. You can ask your question here.
Yeah. So can you run with Python 3? Few of them who are getting the error no module name Dolphin. If you are using Ubuntu, I guess you are using above 16.04 or something. In that case, can you use, instead of Python file name, can you use Python 3 file name?
Yeah, this command. Yeah, this command.
So HP 15 notebook, are you running on Windows Linux app or something, Pranav? No, we haven't come on Ubuntu. We haven't come across this error, Pranav. Sorry. So yeah, just one check. What all of you can do is you can check if the Dolphin is installed or not with the Dolphin version command.
Yeah.
Or you
and
can
I
use,
will
yeah.
Dolphin version. Yeah. So it will show something like this. See here.
Yeah, so it is showing the version 2019.1.0. Else, as Rishikesh previously explained, you can use Dolphin get demos as well and see what it shows. Could anyone run it?
No.
None of you?
So apart from Parnav, anyone? Because Parnav is getting very weird. Why Sarath? Are you able to run with the Python 3 now?
Sujit, what about you?
Hello. I'm Yemi.
Hey, hi, Amsha.
Ah,
Yeah, hi, Sharat.
I'm using Ubuntu latest version to 2020, I think. And in that case, I used the Python 3 demo poison.py also. Then also I am getting the error like.
So have you installed the FEniCS?
Yeah, I checked FEniCS. I have installed that thing.
So did you use those 4 set of commands?
I used the Dolphin version also. It shows that Dolphin version 2019.2 like that.
Okay. Can you use with Python 3? Did you use with Python 3?
Python 3 also. In that case, the error shows that no module named Dolphin. Whether we need to copy these files to some other folder.
Yeah, just check that one. See if that works. So sometimes it behaves erratically, but sometimes it works well out of the box. Could anyone run it? You can reply in a chat.
So
hello, or are you people installing or something?
Hi Pramod, this is Sharath.
Yeah, Sharath, tell me.
So I'm getting errors like if I'm actually I have installed Python 2.7 and then FEniCS, GMesh and Parawave, everything. But when we use this command called Python demo poison .py, it shows that from Dolphin import star no module named Dolphin. But when I check for Dolphin /version, I'm getting the version that has been installed, like 2019.1.0.
Yeah, can you try with Python 3?
Yeah, I did it. So when I do with Python 3, it gives me a random errors like expression F has some errors and
okay, so
something like that.
In expression, yeah, I will show you what is the error for you. Just a second. So in expression, I don't have any expression, it seems. Just a second. Yeah, are you using this one?
Yeah, I expect. Let me check.
Okay, so use this degree. I think this is the missing part in your F.
Comma degree.
Yeah, comma degree.
Yeah, it has comma degree too. In expression.
It has?
Yes.
Oh. Then we need to check. So till now only one we are seeing.
Can you run other examples, see if they work?
Yeah, let me check. Thank you.
Check by mat.
By mat.
Oh, but by mat we have not shared mess.
Yeah, so you can check other examples if not.
Like, shall I check 2D elasticity?
Yeah. Any one of them and see what all those work. If it works, then at least your system is up and running.
Yeah, it's working. 2D elasticity is working. Calling FFC just in time compiler.
Yeah.
It may take some time. It's working.
Okay. Yeah. Good.
But okay. Matt. Okay, fine. It's working for me here. So 2D elasticity is working, but poisons.
Yeah, I mean, other than that, yeah. So there is some. We'll rectify that, but as of now, yeah.
Yeah, so it's fine. Thank you.
So I hope you people have installed and running it. So, or do you have any doubts in code or something? We can help them at those as well. You can ask in a chat box, or you can unmute, raise your hands, and we will unmute you, and you can ask us. Any questions regarding the coding part? The codes are pretty simple. They are just 10 to 15 lines.
So if they don't have any question, Pramod, I think we should explain non-linear thing.
Okay. Yeah.
And then elasticity, right?
Yeah. Then elasticity. Yes.
Okay. So I think elasticity you should explain with BIMAT.
Okay. Fine.
BIMAT, I have written many things.
Okay. Cool.
And here we have displacement, not force thing.
Yeah.
So yeah. Okay.
So BIMAT, did you share with the code at least?
I will
Yeah.
I will
Yes,
share
yes.
the
It
I
is
will run
shared.
code here.
Okay.
No,
Yeah.
no,
Yeah.
code I have shared, but mesh I think I have not shared. So
Yeah.
if you want, I can run here.
Yeah. Can you load the code mesh there so that they can
Yeah.
access the mesh as well?
Okay.
The link is
Okay.
already shared with them. They can download it.
Okay. Just a second. I have started my sharing. Just a second.
Yeah, sure. I'll share the previous code and lost the chat messages. So yeah, the link I'll put up.
Yeah, I have shared that.
Yeah.
It is there in mesh.
Yes. So the biomaterial example, the mesh is loaded through GMesh external XML files. Those are provided in the folder known as mesh in the link that we have
We
Google
should keep
Drive.
in mesh only because I have written here through mesh. So,
yeah, the path has been provided in the Python for that mesh. So don't just, or you can change the
None
path
of
in
your
code.
screens is visible.
Excuse me?
Screens.
yeah, actually I have stopped that. Pramod will share his screen.
Yeah. So shall we? Hello?
Yeah, it's better if one of you show what exactly is happening.
Okay, so can you show the code where I have sent? This one, FEniCS code.
Rishikesh, can you run that your again that code poison.py?
Just a second. I will start share. Yeah. So I have used this editor, so you can use any editor also, so that you will have you will not have to worry about this
indentations and everything.
Indent. So this is the result for the one Pramod has explained. And the code I have shared is here. So the mesh I have shared is here. So I have shared these three files. And I think we don't need to change the path, as in BIMAT file, I have already given in the same path. You can change the path also. So you should remove this part. If you want to keep in the same folder, you should remove this. Yeah, Pramod.
Yeah.
I think you should.
So yeah, we shall proceed with the non-linear. Yeah.
Shall I stop sharing?
Yeah. Yes.
Or
you can
shall I?
you can open the non-linear drive code.
Yeah, non-linear drive code. Yeah.
Can you download it from that? Because it has a lot of comments. They might. Okay, fine. Yeah.
Oh, you want to delete that?
Yeah, because the deleted, the clean version is in Drive. Okay, anyway.
Okay. Yeah.
Yeah. So yeah, before that, yeah, probably I'll show you the presentation, the weak form and governing equation. Yeah. So Rishikesh, can you stop sharing?
Yeah, just a second. Yeah.
Yeah. So just to before going to the nonlinearity, had we if we had if we wanted to extend this 2D problem to 3D, all we had to change was the convert this mesh to a 3D. Instead of unit square mesh, you could have unit cube mesh or something, and then probably the boundary condition for if X, and then you might wanted to just change almost nothing else.
Yeah,
Other than
nothing
the
else.
mesh and the boundary condition, if we had some other boundary condition in third direction, other than that, you need not change anything in the code. So the code is that is one advantage of the FEniCS is that you can go from 1D to 2D and 2D to 3D quite seamlessly. Okay, unlike in MATLAB where you had to do all the juggling again, mathematical jugglery again, or the abacus where you need to model the 3D the domain and everything. So that's one such advantage with that. And now coming back to the nonlinear examples, the same Poisson equation, but the previous Poisson's equation was a linear one. The solution U was a linear. Here the governing differential equation is a nonlinear, right? So because the del U is pre-multiplied with the Q of U, the Q is you can assume something sort of heat transfer problem, right? Where the your conductivity is a function of displacements. Sorry, the temperature themselves, right? So as the temperature is changing, the conductivity is changing. So such kind of problem you can visualize as nonlinear Poisson's equation with F being the heat source or some sort of things. So the governing weak form, the variational forms becomes this way. So if you notice one thing, you can't segregate this out as a bilinear and linear form, because although there is a linear term fv in terms of your test functions, there is no bilinear term as such, because q is again a function of u. So this is what the nonlinearity comes here from, because you are so you can't really segregate out that, so you can't use a linear solver. So for these kind of to problem solve, we can use the Fortran code or C code or MATLAB. We can use a Newton-Raphson, one of the popular solvers that we can easily invoke. With the command we will seeing in the next slide. So we have to, if we want to solve this in a conventional FEM, nonlinear FEM way, this we take it as a residual. We minimize this residual with respect to u by writing a Taylor series expansion, right? And then we construct a tangent stiffness matrix and everything. So all that computation we have to do manual in that case when we have to code it in MATLAB or Fortran. But here we need not. It just segregate itself out. You have the backend FFC and all those in order to segregate these entire weak form, right? So the same again, the same code, the similar code is there. If you see, almost all the components are similar. You have the loading of your importing your the stuff Dolphin and Matplotlib necessary, imposing the boundary condition, deciding the subdomains for applying the Dirichlet boundary condition, meshing it, and then creating a function space. CG is again a CG same as continuous Galerkin or Lagrange, are also known as Lagrange this one, and then you apply your boundary conditions. Then so here is one such example. There was something known as a trial function, right? In the case of the linear examples. So here it will not be a trial function, but it will be just a function. Then you have the test function as usual again. Then you write the weak form f. You don't segregate out as a linear or bilinear form. You just feed as f equal to 0, and our unknowns is u, subjected to the boundary condition BC, and these are the additional parameters. If you omit these parameters, it will take by default. If not, if you want to control those parameters, you can manipulate this function sol. So to use your own inbuilt parameter, I mean to use your own custom parameters. So the Newton-Raphson, the solver we are using with a relative tolerance of 1 e power minus 6. We can also specify the absolute tolerance. We can also specify the maximum tolerance. But in this example, we are only providing the relative tolerance, right? So we are solving the f equal to 0 for the unknown u, for unknown function u subjected to the boundary condition BC with these parameters, right? So whatever the output will be get stored in u. So either you plot those u's with the matplotlib, or if you are running in some remote system or something, you can dump it into the paraview file, and then you can copy back the folder and visualize in your own paraview or something, right? So this is what the nonlinear example was all about. You need not worry about what kind of so you need not worry about what is a form of Q and everything. So that it will automatically take care. Here in this case, we have used the form of 1 plus u square, right? So that automatically will solve it. Yeah, so if you have any questions or something, you can ask me. Running the code, yeah, Rishikesh will show it. If you have any questions, we are open for your questions regarding this one. So could anyone run this example and see it? Any questions? No, else Rishikesh will show us.
Okay, so I think Pramod has explained conversion of 2D to 3D. So I will just show how easy it is in the code. So as you have seen already the code demo Poisson. So here we can see we had unit square mesh, but instead of unit square mesh, we just need to provide 3D mesh. To construct 3D mesh, we should write unit cube mesh, and then dimensions would be this one. So this is the division, and then the cell will be 1 cross 1 cross 1, and then it will have 32 cross 32 cross 32 divisions. And then once you run this, everything is same, so no need to change anything. It will just solve, and then once you try to see this, we'll be able to see this in 3D. So I have used paraview here to post process. So it is very super easy to go from 2D to 3D. But as Pramod explained, if you want to write in MATLAB, it will be a bit tricky, and we need to do lots of things. So now I will show the nonlinear thing. I think this is the same. Yeah, this is the same.
Hello, Rishikesh. There are two questions in the chat. What is relative tolerance from Vinod?
Yeah, Pramod, can you please explain? Hello. Hello.
Pramod, we are not able to hear you.
Yeah, sorry. I had muted my mic. Yeah, so the new relative tolerance is in the context of Newton-Raphson. So if you are aware of the Newton-Raphson, it's an iterative procedure. So where there is some stopping criteria where you need to stop, okay, if your answer is fine enough, then you will stop the iterations. So in that context, the relative tolerance is used. So it is a measure of how much is a change between the successive iterations relative to your absolute solution. So that is what the relative tolerance is. Most of the simple cases, you can omit those relative tolerance. But in some case where your convergence is very hard to achieve or something, you might want to play around those parameters. relative tolerance, and there's something known as also absolute tolerance, and then the number of iterations and all those things. Yeah, so if you know the Newton-Raphson, it is assumed that you know a bit of Newton-Raphson. In that case, the relative tolerance would have been clear. I hope I have answered, at least given you the direction, in order to get back to you later on. Yeah.
And another question, context relevant, please explain voxel mesh. Are you aware about this, Pramod?
No, I am not aware of voxel mesh. I don't know. Yeah, sorry. Yeah, Rishikesh, do you want to show the 3D how they're running and everything?
Yeah, there's one more question. Can we implement adaptive refinement in FEniCS?
Yeah, it is possible.
Yeah, so Rishikesh is expert in this. Yeah, I think Rishikesh have probably tried it, and
we can do that. Yes.
Yeah, so the adaptive refinement is possible in FEniCS. I think there is a demo or tutorial already available in documentation. And there you can probably use adaptive refinement.
So I think I have shown this one, Pramod. 3D Poisson already.
Non-linear as well?
No. Okay, so just a second.
Yeah. Can we see or edit the functions used in these codes? Yes, you can, but that's very advanced stage. At least I have not come to there yet. Rishikesh, any experience with the editing the functions?
Also, you can write your own indicator to do the refinement. That's what they want.
Now it is another question. Can we see or edit the functions used in these codes? Not related to adaptive.
Okay, so we can edit this ones and whatever we are defining here, but I don't have much experience behind the back. But I think you can do that. That's why they have implemented GUIGMS, IGA. So at an advanced level, I think you can do that. So for the non-linear, I am defining this. So this is the mesh I am modifying. I think we have X0 and this is fine. I think. Don't need to change anything, Pramod, right?
No.
I think for the support, we don't have much support for 3D, so we need to use ParaView. Yeah, it takes some time because I'm running in my local system.
Yeah, so to modify or edit the functions such as function space, it might be possible, Jha, but we haven't done it. So I can't much comment on it.
Yeah, so this is the results for non-linear Poisson. Why we prefer ParaView is we can easily manipulate that the plot which you want to, which face you want, which along the line you can plot everything. That's why it is very nice to show in ParaView. Yeah, so this is the result for 3D non-linear Poisson.
So any questions regarding any non-linearity or something? Yes, Edwin, parallelization is possible in FEniCS. Yes, with Empire. Yeah.
Yeah, actually, I will show you how to do this, how to run actually now.
Yeah.
So for example, most of the code here in demo is parallelized. So you just need to run MPI run minus NP. So let's say I'm using 3 cores and then Python 3 and then demo Python. It is asking something. Yeah, so it is done. So it has used, if you are seeing here, so let's say you are going to see here process 0, process 2, 1. So it has taken 3 cores. So if I run on 4 cores, my domain will be divided into 4 and then it will run. So I will show you the plot which we have generated using these 3 runs. So how system is going to divide, that I will show. Yeah, so this is the complete domain actually. But as we have run in parallel, so FEniCS will divide into 3 parts. So first part is this one. Second part is this one. And third part is this one. So it runs in 3 parallel cores, and then it throws the solution in a one file. So in the 3 files that you can see, and you can also see in a one file. So let's say, for example, here. So this is result. Yeah. So it will throw in single file. So this is easy to so visualize the data here. So in ParaView, you can easily visualize the data either in all the simple processes in individual process, and then as a whole. Yeah. So this is the way you can do that parallel. So just you need to use this command. So I think if you want, you can try this command. But for your code, you need to think about some time. Yeah, thank you.
Also, Rishikesh, Jatin Deep Singh has asked one more question related to that. Can you show explicitly where in the code we have used MPI parallelization?
Actually, it is inbuilt, so we have not said anything now, as of now. So it is written in C++ behind the back, and there does parallelization. So we are not doing anything here, but we are provoking here by using this MPI run. Invoking.
So just the final running, the command is different. That's it.
Yes, command is different. If you don't want to use this in parallel, just we were using this one, Python 3. But here we want to use for, let's say, for 4 cores, just we need to change the code and then we can run them. Because most of the demos are in parallel. And we are using demo. So
there's one more question. Is it possible to restart a simulation from where it stopped if the computer crashes?
I think we can start with the initial solution that we need to take it from the .pvd. I think that is possible, but I have not tried. I have seen we can do that. If you have, let's say, your domain solution, let's say you are solving transit problem, then we can start it using your .pvd file as an initial solution.
But it's not possible to start from the middle, wherever it is just before it crashed.
Yeah, no. No. You can start, but as you have saved previous data in .pvd, so you can take as an initial guess, and then I think you can proceed.
Okay,
but
so take the final,
possible.
Take the final one from the last simulation as the initial one here.
Yeah.
Next question, is the SMP shared memory parallelization also implemented?
Yeah, I don't have much idea regarding this. Sorry, Chetandeep.
I think that's it in the questions in chat, and there are no questions in the.
Okay, so
there are no
Pramod, can you
raised hands
explain
also.
another one? Next
Yeah.
demo.
So far we have seen was a scalar field variable, right?
Can I stop sharing?
Yeah.
Or will explain on my system itself?
Yeah, on your system also is fine, no issues.
So okay, I will open then BIMAT.
Yeah, so far, shall we go with the BIMAT first or elasticity?
Yeah, anything
Okay,
is
we can
fine.
do it together. That's no issues. They're just the material properties are different.
Yeah, it will be of interest for somebody. That's why.
Yeah. So far we have seen whatever the unknowns we had was a scalar field problem, right? So the vector field problem is something. If you have known the elasticity example, let's say your divergence of sigma equal to 0, where sigma is dependent on your strains and your unknowns are in 1D case it is just ux. In 2D case the displacement in x direction and y direction, and in 3D case displacement in all the 3 direction. So in that case. So the how code looks like it's something shown in 2D underscore elasticity.py, right? So yeah, you probably want to run the case and see in paraview, and you select the UX, UI, and UZ, and you might be able to see the displacement. Okay. So yeah, just can you, Rishikesh, can you run the code, or
Okay.
can you open the presentation in the drive?
Just a second. Is it here? Yeah.
Yeah. Yes. Before that, the weak form. Yeah.
This one, right?
Yes. Just go in present mode. Yeah, so this is what the governing equation looks like. Del dot sigma plus f equal to 0, and rearrange them. So minus in domain, and the constitutive equation sigma equal to 2 mu epsilon plus lambda trace I epsilon, and then epsilon being the symmetric part of the displacement gradient. So that is how you can recast then later on sigma into that form. So the weak form looks like the line number 5. So sigma inner product with a divergence or a gradient of v, where v being test functions, and then again the right hand side your boundary, so your source term f dot v, and then the boundary terms. So the bilinear form, again this is a linear problem, although a vector field, but a linear problem. So this bilinear forms is left hand side, and the right hand side is your linear form, where the sigma is in terms of the Lam's constant, lambda and mu looks like that one. So, and the linear form. So essentially, I mean, this is the crux. If you know the governing equation, if you know the system of ODEs and PDEs, write the weak form and just write that abstract variational form in Python. That's all you need to do. So this is what it is, and that sigma and L will be coded in your the Python, and remaining will be in the similar terms. You are loading the mesh, you're applying the boundary conditions, write that different variational form, and then again dump back the solutions into your PVD and everything. Yeah. So more or less the same thing. Additional, just the variables are defined gamma, beta. Those are just for domain definitions. Other than that, everything is just the same. We have seen the trivial one.
Yeah, just only change is vector function.
Yes. Yeah. So the unknown variables we had was a scalar. So there we were using the function space, but here we have the vector. So we will be using the vector function space. Right. The more detail you can see it in documentation. Yeah. Or in the book as well, the details have been given. So yeah, this is what the code looks like. Yes. So Rishikesh, do you want to run it? Oh, he has already run it probably.
No. Oh, actually, I have not plotted anything. So
yeah.
Yeah, Pramod, I think you can answer that one. Meanwhile, I will.
How can I apply a force at a particular point in a code? Concentrated force. Rishikesh, I forgot. Can you tell me?
Okay. I think we need to add point wise. Yeah, he want force or
force. Yeah, so Vinay, what can you do is probably you can write a Dirac delta function.
Yeah.
At that point coordinate, and then you can impose that as a sort of a body load. Yeah, I hope Vinay, that answers your question.
But if you have to apply displacement, it is easy. Just you need to write here something like this: method equals to. It will apply point wise. So let's say you are applying only on one single point displacement. So this way we can do that. Yeah. So this is the problem we were solving.
So the example, no, we don't have any example, but you should be able to find the example in either the documentation or on the internet. See, one of the positive things, it has a huge support, so you should be able to find somewhere someone must have done the problem you are encountering.
Yeah, so I think somebody has already interest on BIMAT, so I think you can explain BIMAT, Pramod.
Yeah, so the BIMAT, as someone probably asked at the initial, so see, as we have seen, the scaling from 2D to 3D is quite easy, from 1D to 2D. In the same way, doing the material discontinuity problem, like you have a two-phase composite, let's say, or for that matter, functionally graded materials. So in that case, the weak form, all the material properties just change. So doing that, implementing that is quite trivial. So you need not again model or anything. Just in a mesh, specify in the code that where all you want to use, let's say E1, Young's modulus of material 1, and Young's modulus of material 2. So once we do that, remaining rest all, everything remains the same. So you need to load the mesh, and you need to say that, okay, this part of the mesh, this part of the domain is material properties 1, and this part of domain is of material properties 2, and then that is how. And that is what the example Rishikesh is showing here. So he is loading a mesh materials and boundaries, the mesh from GMesh in a materials where he's showing the physical region, right? The surfaces where the half portion was E1 and other half portion was E2. And the boundaries are sort of a facet where you are applying some sort of boundary condition. So the mesh function, and then those, if you use anything, the file name physical region, it shows the bulk of the volume, right? And the facet region, it shows the boundaries. On the boundaries, the numberings and everything, the information will be there in that particular file. The BIMAT underscore facet underscore region.xml will have the boundaries associated information, and BIMAT underscore physical underscore region.xml will have the information associated with the bulk of the volume. So, okay. So once we load that, and he is assigning the material properties using the class name as AL, right? So we are then he is just initializing it, and he is passing the arguments, and then he is giving the material K0 and K1. Later on, he is just saying that, okay, so if you remember while meshing, he had given one portion of the domain was assigned as 1, and other portion was something other than 1. So he's saying that whatever, so what the GMesh does it for each and every element, it assigns that number, right? Let's say if I have divided the entire domain into two parts, subdomain 1 and subdomain 2. Subdomain 1 I'm numbering as, let's say, X, and subdomain 2 I'm numbering it as Y, right? And when I say that, okay, as long as you are loop through the cell, and if the cell index is something X, assign that material properties, let's say K0, K underscore 0. If not, assign something K underscore 1. If you are only biphase material, if you are more than that, you can use more if and else conditions for corresponding all those materials. and there he is using E1 nu1 and E2 nu2, and then he is passing those E1 and nu, those two material properties E1 nu1 E2 nu2 to the classes AL, right? And then those material properties will be assigned. As simple as that. So that around 7 to 8 lines of codes does that function. Remaining everything else remains the same. Rest of the code remains the same. Yeah. Anything you want to add?
Everything is same.
Yeah.
Everything is same. Yeah. So this is just to show how we have constructed E. We need to project back to your space, and then we can easily show how we have constructed your E. And one super cool thing is if you want to write functionally graded materials. Let's say, for example, I have a system where my E is varying from bottom to top. So do we have any example here? I think will not be able to see that, right? Okay. So let's say, for example, if you have a domain in which material is grading in y direction from 0 to 1. So if you need to write that, we can easily incorporate here like this one. So let's say E. Yeah. So if you plot this, it is varying in y direction, and it starts from it starts from E0, and it multiply with your distance. So if you plot E, then let's say if you can. Yeah, so now here I have dumped my E value in K, and then once you see this, so here I have started with E0. My E0 was yeah 210. Yeah, I have started with this, and then we have gone to so this is the way we can easily incorporate functionally graded material property within the simulation. Pramod, do we need to explain transient now?
No, I think we are running short of time, Rishikesh. If they have any questions regarding this, we can take the question. Nonetheless, we have shared the code of transient. You can go through them.
Explain, I think, one transient, that's all. So that they will have feeling how can they discretize time, because till now they don't have time discretize something.
Yeah. So just to briefly describe about the transient problem. If you see, let's say you take a heat transfer equation where you are on the left hand side, your single one order derivative with respect to time. imagine U being the temperature. So derivative of the temperature equal to, and the right hand side you have again the classical your diffusion equation del square U plus F subjected to the boundary condition UD and subjected to the initial condition U naught. So in FEM we have seen that the temporal terms are discretized using the finite difference method, right? So depending on whether you wish to go for implicit or explicit, the left side term alone will be discretized in terms of the time. So del U by dou T will be discretized as UN plus 1 minus UN by delta T, and remaining everything remains the same. Just go on with the weak form and then just put the same variational form, put it into your Python FEniCS code. You should be able to run it. When you run it, you will be able to generate a PVD file. In that PVD file, there will be multiple VTU files, right? So, and then you can load that and you can see the time series as Rishikesh has shown in his crack propagation in mode 2 shear problem, right? So the entire animation, you might be able to see it. So for every corresponding time, you will have some counter plots, and that there is where the beauty of ParaView comes in, right? You will be able to see the multiple. Otherwise, in screen, if you use the matplotlib, it will just those will be keep just popping up, right? Okay. We have shared the code. Just have a look at it later on. If you have any codes, you can doubts or anything, you can always write back either to Professor Ratna sir or either to Rishikesh or to me. We will be more than happy to help you out, right? So yeah, regarding the code part, if you just see on the line number, the line where is being highlighted, you have to just define the times delta T and everything. Once you define, you just write the weak form. That is all. Other than that, there is no change. Just put up the whatever the finite difference you are discretize, just put up those, and then just go ahead with your remaining all the stuff, and then just you will be looping from end until the range of num steps. For every time step, you will be solving for a particular space, and then you go ahead with that. Yeah, can you please explain the implicit and explicit time integration techniques FEniCS have? See, it doesn't have it. You have to code it. So that is what we are coding. Rishikesh, can you go to the slides? Yeah, to answer to Sanjay's question, if you see the way we are discretizing dou U by dou T, that's where the implicit or explicit is embedded in. Right hand side, we are keeping in terms of n plus 1. So that becomes an implicit for you. If you write right hand term in terms of a known quantity is that an UN, it becomes an explicit. And you can probably put a play with say other variations like Crank-Nicholson or sort of things by keeping the theta parameter and everything. That's quite possible. So that's the way. So that's the thing we need to code. Just probably one more addition of a line. Other than that, everything remains the same. So does that answer your question, Sanjay? Yeah, thanks. Yeah, so any other questions? We have around 5 to 10 minutes. We are happy to take. If you have any later on, please go through the documentation and everything if it is necessary for you. And then if you have any question, you can always mail to sir or Rishikesh or me. We have given the mail IDs at the end of presentation. You can mail us. You can shoot a mail. That shouldn't be a problem. So we are happy to take any other questions. Yes, we will be sharing the PPT with you.
If you have any question, you can ask now. So I think we have 5 to 10 minutes. We'll be happy to answer.
Hello, I have shared the feedback form. Please try to fill it in your free time. And as Vishka said, if any of you has questions, you can raise your hand or you can ask in the chat.
Yeah, we have some time, so we'll be happy to answer some what are the possibility we have in FEniCS. That also we will be able to answer from our context, whatever we have done till now in our research and whatever experience we have with FEniCS. So I will be happy to answer. And during the research, if you face something, we will be happy to provide help.
Yes,
Yeah.
the tutorial recording will also be shared, Anup.
Akhil, this form is not able to, Manisha, he is not able to access form.
1 second, let me check. It opened for me easily. You need to
Even I could open it.
It might show that it's coming from external site or something. Just click on continue, and then you should be able to see.
Yeah, try contacting the owner of the form. Yeah, it seems many has issue.
Just a second, I'll check with sir and then I'll inform. And till then, if any of you has questions, you can ask. I think Paras Kumar has a question. He has raised his hand.
Yeah, please.
Am I audible?
Yeah.
Yes.
Yeah. So, Rishikesh, I was wondering, like, when you model this fracture in functionally graded materials, so how do you then take care of this interfacial or cohesive kind of delamination or whatever?
Actually, I have done using phase shield, so I don't need to care about the tracking of crack growth. So the method automatically does that. So I don't need to.
I'm also working with phase field, but don't you do something like a delamination then extra on top of that, or you just say that phase field works for everything?
No, actually, no delamination. We say in fracture term, but regarding actually in phase field we have just 2 phases. So once it fails, it will be 1. So in terms of fracture mechanics, we say delamination along the interface. But here we don't need to track it. So in FEniCS we can do that easily. But if you have to do with the discrete approach, then we need to track it always. And then we need to, if you are using XFEM, then need to add some discrete function, which is not possible, I think, in FEniCS.
Okay. So you are just, doing a standard phase field kind of thing. You don't do anything special when you go across material boundaries. So you do as you would do for a homogeneous material.
Yeah. As of now, we does that same, but we have also proposed another way. We can deal with the how we can reduce the fracture toughness of interface, so that we can grow the crack along the interface, and then we can explain the branching phenomena. But that is in the framework of phase field. So
yeah, but then there you kind of say model this interface as a diffuse interface of a given thickness and some sort of variation of the properties in that.
Yeah. So I have diffuse interface now, so we can treat as a diffuse.
So you
interface,
don't have
no discrete.
Zero thickness interface, so to say. You diffuse that.
Yeah. I diffuse within the length. So my length scale may be probably same as of fracture length scale.
Okay, so you take that diffusive thickness also same as this LC, what we use for the phase field.
Yes. As of now, but we can for sure treat differently.
Okay, cool. Yeah, cool. Thank you.
Okay, thank you.
Yeah, so the guys' feedback form is accessible.
Pramod, can you answer this one? What is parallel of
What is a parallel of a UMAT in FEniCS? Yeah, I mean, See, essentially, so you may want to do some sort of plasticity or large deformation, which you can do with the UMAT. You need to code those constitutive equation in FEniCS. That's where the things can get trickier. That's where the limitations can be apparent in UMAT. Sorry, in FEniCS, because later on you need to have the robust solver and everything. So it may not be always easy to do at least those things in FEniCS. So yeah, parallel of a UMAT, you need to code those constitutive equation in the Python. There is no parallel version. There is no parallel of UMAT in FEniCS. Also, in the phase field code already available in the standard library. See, the phase field, the way Rishikesh is talking about, is again another set of equation, right? You have the elasticity equation along with you have another damage varying equation. Yeah, many people and including our group have made some of the codes public. Rishikesh
Yeah,
code.
my group, my code is in public, so I think you can download using my website.
Yeah.
Or from the GitHub.
Yes. So, and you can also browse through Professor Ratnasar's website, and you can see Rishikesh code and other codes associated with that. There are many FE codes. Why should I use this? Yes, that's right. There are many FE codes. Why should I use this? See, every abacus answers has their own, advantages, pros and cons. In favor of FEniCS, it's firstly open source. Secondly, Python based, so very easy to code and everything. Thirdly, scaling and parallelizations are quite easier. Fourthly, as a beginner, if you want to code some sort of simple equations, you do not scratch your head with a MATLAB or a custom equation where it may not be easily implementable in abacus, subroutines and everything. Console being commercial, this being an open source, and with a less steep learning curve. See, these are the things that go in favor of FEniCS.
Yeah, one main thing I can highlight is here we can directly provide the weak form and then FEniCS does the job. But most of the commercial software and open source software, we need to provide a matrix and then they can do the job. But here we are just providing the weak form, variational form of the system, and then it does automatically your job. And it is very easy to do that.
Yeah, see, it's like in a way you can think of this one as writing a weak form on a paper, convert into a Python code, and it works out of the box.
Yes.
Right? But in the case of Deal2 or MATLAB, you need to use all sort of shape function, numerical integration, and you need to build it from the scratch, as Professor Ratna said at the beginning of answering one of the questions. Yeah, so those are the things. As an expert, why should I use a FEniCS as an expert? I mean, see, still being an expert, you need to, you may not always want to build things from the scratch. I think that's how it probably helps. Yeah.
And as long as we are working on conventional FEM, we can do that job using FEniCS. But only thing is, if you are going from advanced FEA, like a scale boundary or something, we need to do your own coding.
Also, there was a question regarding, can you comment on XFEM and FEniCS?
Yeah, Rishikesh.
XFEM in FEniCS is not possible because we need, FEniCS is based on standard elements, a standard conventional element, but in XFEM, we need to add enrichment function on the approximation space. I'm not aware about anyone has done it already. XFEM in FEniCS. I think that is need to check. Writing UMAT for plasticity problem. So plasticity problem we can easily tackle in FEniCS. We don't need to write anything explicitly. So I think we can tackle it easily in FEniCS. No need to write any UMAT thing. Because here we are just defining our D and the algorithm for solving. Yeah. Yeah, people are working on this area. So plasticity we can do easily. I'm not expert in that way.
There is one more question regarding biharmonic problems like plate bending problem, how FEniCS chooses shape functions like C1 continuity elements.
Yeah, we can construct C1 continuity. Pramod, do you have any experience with C1 continuity?
I think just to add to what Rishikesh said, probably you can use the element library. There are a vast number of elements available in FEniCS. If you just go through the documentation, you should be able to just invoke instead of Lagrange or continuum Galerkin. Probably you should be able to invoke and employ.
Yeah, here we have said, let's say we said P or Lagrangian polynomial and or CZ. So this is C0. But if you want, we can invoke through this one here. Many different elements are available in the library.
There is one more question from Jacob. Is your phase field code implemented as a cohesive element?
No. Jacob, no, we have not used cohesive elements. Now I'm working on something like diffuse interface. So where along the interface, I will use phase field as a tool to reduce the fracture strength or increase the fracture strength. So answer to this question is no, I have not used cohesive elements. Is there any question now? So shall we summarize this, whatever we have presented today?
Yeah, Rishikesh, you can go ahead. Yeah.
Yeah. To summarize this, we have given a starting point for the FEniCS user. So if you know how to write weak form, then after this talk, we will be able to write your own 1D, 2D, and like I explained, you can extend to 3D. So this presentation is just for starting, and then we have explained how we can do pre-processing, post-processing, and do the processing thing using the FEniCS. I think you'll be able to write your own code after this talk, mostly. If you have any questions, I will be happy to answer along. Maybe you can send an email, me, Pramod, and you can also ask. You can send an email to Ratna sir. We will be happy to answer. Yeah, Pramod, if you want to add anything, please.
No, nothing to add to further that. So guys, thank you very much.
Yeah, thank you very much.
Yeah, let me know. Yeah, you can, as Rishikesh said, if you have any things, we will be happy to help you. Just shoot us a mail. So Akhil, we are done from our side. Akhil?
I think attendees can leave now, and please kindly fill the form. I am stopping the recording.
Okay then, Akhil. Thank you very much.